Okay, in the last video, we found that the differential mode gain of this source-coupled pair with a current mirror load was equal to GM1 or 2 times the parallel combination of RO2 and RO4. Now, we're going to be using these amplifiers typically in a feedback mode. And in feedback, more or less, the feedback will force all of the nodes in the circuit to operate relatively equally. So for instance, we can say that the output node will end up being approximately equal to our current mirror node, B sub A. Now, if this is the case, if they're equal to one another, we could draw a virtual short between the node VA and node VO. Now note, we're also going to be talking about common mode gain, which means that we're going to be explicitly talking about the inputs of the two differential pair transistors, M1 and M2, being equal. So we have VI1 is equal to VI2. And if we have this, we have a perfectly symmetric circuit. M1 is and M2 are in parallel with one another, and M3 and M4 are in parallel with one another. So we can make an equivalent half circuit. Now, ultimately, what we need to do is find what the resistance looking up along this red line is. We can say that the resistance looking up is into a parallel diode connected transistor consisting of the parallel combination of M3 and M4 that are both diode connected. So R looking up is equal to 1 over GM 3 or 4, 1 over 2 GM 3 or 4 in parallel with RO 3 or 4 over 2. The factors of 2 are due to the resistances being in parallel with one another. So we can draw a half circuit equivalent where we have a load resistance that's equal to 1 over 2 GM 3 or 4 in parallel with RO 3 or 4 over 2. Generally, we can assume that this RO 3 or 4 is much larger than 1 over GM, so we can ignore the much larger resistance. Now, we're going to combine M1 and M2 to make a transistor that is approximately twice as big, and this means that it has RO1 or 2 over 2 for a resistance, and that the total GM is twice the GM of a single transistor. In other words, 2 GM 1 or 2. So here's our equivalent half circuit. Now we know that big GM for this circuit is equal to 2 GM 1 or 2 divided by 1 plus 2 GM 1 or 2 times RS, where RS is the impedance of the current source. We know that our total resistance is going to be very similar to what we saw before. RO1 or 2 over 2 times 1 plus GM 1 or 2 times RS in parallel with the resistance looking up, which is 1 over 2 GM 3 or 4. Now, we expect that the left half side of this equation is quite big compared to the right half side of the equation. In other words, we have a parallel combination of a small resistance with a big resistance, so we can neglect the big resistance and just say that this is approximately equal to 1 over 2 GM 3 or 4. All right, so we can now write our common mode voltage gain, product of big GM and RT. Now, we can see a couple of things. Our common mode voltage gain is small when GM1/2 is smaller than GM3/4, and also small when RS goes to infinity. Now that we know our differential mode and common mode voltage gains, we can find the common mode rejection ratio. So substituting in what we had on the prior page, our common mode rejection ratio is equal to RO2 parallel with RO4 times 1 plus 2 GM1 2 times RS times GM3/4. So we can see to increase the common mode rejection ratio, we can either increase RO2 and RO4, we can make RS very large, so we can increase it, or we can make GM3/4 very large by increasing it. Now the last thing we want to look at with this amplifier is that we have a differential input and a single-ended output, so we need to figure out which terminal is the non-inverting terminal and which terminal is the inverting terminal. This amplifier is the basics of an op-amp. In fact, this is called sometimes an operational transconductance amplifier. It's called that because it doesn't have a low impedance output stage, so it's not an ideal voltage amplifier yet, but it does have a differential input and single-ended output. So we're going to do this by doing a basic check. I'm going to put a plus delta V into V1. And if I do that, it's going to cause more current flowing down through the drain of M1. In other words, it's going to cause a plus delta I flowing down. Now that plus delta I is going to get mirrored by M3 over to M4 and cause a plus delta I flowing down from the supply towards the output voltage. Now the supply voltage is at a high potential, so this current flowing from the high potential towards the output voltage is going to increase the voltage of VO. In other words, it's going to cause a plus delta V at VO. So we can indeed now say that the non-inverting terminal is VI1 and the inverting terminal then would have to be VI2. So ultimately, we could use our basic op-amp symbol, and we would know that the plus terminal was from M1 and the minus terminal was from M2. All right, so we'll stop there for the day and talk to you later.